thank you for hosting me here. I'm glad to be in this room which appreciates epistemics. Okay, and I'm going to present you a new paper which I thought about for quite a while. So here is motivation, right? So in non-cooperative game theory, we have many solution concepts which were proposed over decades, and oftentimes they were proposed in a mathematical way, sometimes without even discussing whether or not they are logically consistent and when to apply them. Basically, here is a solution, use it. Okay, but now, okay, so we want to understand, okay, so which solutions are good, which solutions are not, and when to apply. And epistemic theory aims to help with this question in general. Okay, so for example, if you can provide epistemic foundation for a solution concept, then at least it tells me that the solution concept is logically consistent, not contradictory. And another thing is just looking at the conditions in the foundation, we may estimate whether or not we think it's applicable in a certain situation or not. Okay, so now this is why we study epistemic game theory.
But is logical consistency a real concern or just, I don't know?
Well, it's just okay, so if you tell me a player behaves in a certain way, I want to ask, okay, so if this person is possible to think logically and not without self-contradiction in his head, so as to behave this way. If you couldn't find me such a story, then I say that maybe there is a problem with the solution because you're not describing a logical person.
For real people, it's a real concern.
But you mean a consistency in the sense that his considerations do not contradict each other?
Yes. So for example, okay, so think about stable equilibrium of Bernoulli. So they impose quite a lot of desiderata. For example, you want backward induction, but then at the same time you want two kinds of forward induction, like iterated dominance and forward induction per se. And to get three of them, mathematically is impossibility, that's why they have a set instead of a point, right? But then also logically is impossibility because you need to think about, so suppose you see somebody deviate, and you need to tell three things at the same time. That was a trending mistake, or maybe that was a signal about his future behavior, but in two different ways, and it's kind of like doesn't add up into a single person mind. That's another problem with stable equilibria, right? So they identify that it's mathematically impossible to have a single solution concept which satisfies all of these properties. But I say from epistemic theory, we also see that it's logically impossible for a person to think systematically in these three different ways at the same time. It's a bit schizophrenic. Okay, so now, but also, you know, sometimes we look at foundations, say Nash equilibrium or rationalizability, and we ask, okay, so what does a person need to think or know in order to play this way? Is it demanding, is it not? In certain situations. And this may help. I'm not saying that it's indispensable or it's often powerful, but okay, so this is what I think epistemic theory aims to achieve, at least in my understanding. Yes, now, so this is the motivation why we study it, and this is what I want to present. Yes, so I want to present a brand new framework, which I hope to convince is going to be a very tractable and transparent way to study epistemic foundations. Yeah, at least for me, it's intuitive. Okay, but I've thought about it for quite a while, so I'm not sure how for others. Okay, so let me just give you a preview, several slides of how the model works and what I'm doing in the paper, and then we will go through the paper and see how much we cover today. Okay, so basically, I'm thinking about a player who is participating in some kind of strategic situation, maybe a game, maybe something else. But okay, so he needs to make a decision. And how do I describe the situation? I say the player is exogenously given a set of statements. Okay, so I don't know where these statements come from, how the player acquires them. I just look at this point in time at which he already has the statements developed. Okay, and he takes the statements as given and needs to think about them, needs to analyze, and needs to make a decision as a result. Okay, so what the statements are? They are lists of statements which are written in a formal language. So far informally, but each statement has the following form: the player himself, then some verb, like know, assumes, believes the probability P and so on.
That's called modality, no?
Epistemic modality, yes. Modal verb for epistemic modality, and then some proposition about the world, about the situation in which he is. For example, I know that you are Russian, or I know that you believe that I am Russian, things like that. Statements like that. Okay, so he takes this list of statements and then can analyze them in roughly the following three steps. So first, he needs to work them into a decision problem, kind of like a sandwich decision problem.
Small question. So the statements are about the player himself?
The statements about what player himself thinks.
So
Could be about
as a
himself.
player, I receive statements about what I know, what I believe, what okay, and it's true.
That's sort of like the player takes them as given and then he works out as a computer. I'm not asking how the player concludes it's true or not or how he acquires them, but I'm just looking at the beginning of the game at which the player has this knowledge, belief, or assumptions, or all these things.
So just to be sure that I didn't miss anything, why do you describe it as a situation where the player receives a list of statements instead of describing the game in which we as researchers know the state of the player?
Well, just because first of all, I'm not sure if the player thinks that he's playing a game which is common knowledge, for example. I'm going to be modeling what it means to know a game as well. Unlike other epistemic frameworks, I'm actually going to be modeling what it means a player knows a game, what he thinks is common knowledge of the game.
But why should the player read these statements?
Well, it's just because ultimately the player is the object of study, right, in game theory. We are thinking about the player.
But why you describe it as if the player reads these statements? Why not to describe what does the player know, what does the player assume, what does the player believe? Why you describe?
Okay, so I'm not sure. Like this is just how it works. Okay, so.
Okay.
These facts can be about the other players,
Yes.
what they think, what
Yes.
they choose.
Yes. That's yeah, there's going to be a lot of choices which I make in the model, and not all of them I can explain why I chose this way. The best which I can tell you is just the model which I'm going to present is just when I play a game myself, strategic game, like cards or other things like driving the road, this is roughly how I analyze it. This is kind of like, this is how I would think. Maybe you disagree, that's fine, it's just
No, just the fact that he receives this statement is irrelevant to the game. That's what I'm trying to understand.
What do you mean irrelevant?
You can describe the game alternatively by saying this is the belief of the player.
Maybe we should.
Okay.
That's not clear to me.
Let me give you.
We haven't
Yigal,
started.
I guess you understood. I'm not.
This-
No,
This
don't
is why I'm
criticize, we
asking.
have not seen yet.
Yeah. So far, first few slides are going to be informal, and they're going to be a little bit more formal, and then going to be the completely formal game. Right? So there's going to be a lot of layers. I guess now, so what the player does, so first he constructs a decision problem, Savage-like decision problem, how we do it in decision theory. You have a set of acts, and independently from them you have a set of states of nature, and only in combination they generate a consequence or payoff. Okay, so exactly as in decision theory. Then after that, he forms preferences in according with his beliefs and according to his assumptions, these epistemic statements. And then finally, once he has these beliefs or preferences or acts, he chooses the one which maximizes his
I mean, preferences, beliefs about states of nature.
Yes. Well, for example, if he's a savage type guy, it could be usual probability. If he's BBD, he could do LPS or Gilboa-Schmeidler, he could have several priors. All these things are completely, the model is going to be very general, you could plug in many things. What's going to be uniform within the model is going to be a procedure, an algorithm, for how I assume a player thinks how he works them out.
The preference is over acts or over acts and states?
You could plug in any decision theory model if you like. You take
But in your model, you need to have preference over either over the acts or over the acts and the states.
no over acts.
Over acts alone,
Okay.
independent of the states.
Well, look.
The acts are functions of the state.
Actions, yes, it's states to R or states to consequences.
Okay. That's how you define it.
Yeah, yes. Like in Savage, like in Uncle Mama.
Now I understand.
Okay, so now, so far, that's how it goes. And the critical modeling assumption, and the one which makes it everything instructable and inductive and finite, is that I assume that the player has a finite level of reasoning, which is, pretty close to how they model in behavioral cognitive hierarchy models. Like I have a 5 level of, like when I have a 0 level of reasoning, I'm a completely rational monkey. I can pull any lever. Okay, I can play anything. I don't think. But players with level 1 or 2 or higher, they do engage in the previous algorithm, right? They do all these 3 steps. And what separates level 3 from level 4 is just a player with level K, when he computes possible omega, possible states of the world, he considers all possible states of affairs for his opponents when they are levels between 0 and K minus 1. It means that, okay, so if I level 5, I compute what you do when you level 0, 1, 2, 3, and 4. If I'm level 6, I compute more. I need to do a lot of more recursions.
So you should form preferences also for the opponents.
Computations, okay, so what can opponents possibly do? I need to compute, okay, so say I'm level 5, I'm thinking about, okay, so you may be level 4, what is possible for you to do?
To do mean the actions that I choose, the act.
Act, and also at the same time what kind of epistemic picture or state of statements you have in your head, and all these things. Okay,
So just to be clear, the level means how many times
yes.
I think about what you think, about what I think.
Yes.
This is the level.
Yes. Yes. And usually doing such recursions is tricky and complicated, and I wouldn't expect many people and myself to do more than 2 or 3. Okay, but okay, so in model I consider any level between 0 and infinity. So, but then
Everyone thinks between 0 and 3 and then infinity, right?
Yes.
But so when you play Centipede, you think that you don't do more than 2 or 3?
Well, the centipede it's okay.
Yeah.
So the level may depend on the game. I think when you apply, but okay. But I assume for now that it's okay. So the player comes and it's also fixed and it's exogenous. Okay, so maybe somebody could extend this model and try to endogenize. There are papers which do with level K. They try to endogenize level 5.
This concept of level K player is a well-known concept?
Yes. I'll have it's a known concept.
Decades ago.
Yeah, it's okay. So now, okay, so here is the main object of study. Here's how I work through the model. It's gonna be a prediction correspondence. So it takes as input a name of a player, a type of his preferences. Okay, so say he's LPS, or he uses max-min preferences or some other preferences. Decision theory type. Then his level, and then this set of statements, which I call epistemic picture. Okay, and it spits out the sets of possible decisions or strategies the player may choose. Okay, so that's kind of like what we really in theory trying to do. Okay, so we're trying to look at the player and ask a question. Okay, so what can he possibly do?
Strategies are acts, or is that the same thing?
Well, in game theory we call them strategies. When we translate them into decision theory, they're usually called acts. I use them synonyms.
What I'm missing here, since the player is also reasoning about the other players, shouldn't the optimality type of the other players also enter into?
It will enter, through how he calculates what's possible for them to do. For example, he may think, okay, so he's playing against somebody whose usual expected utility maximizer, then this guy wouldn't play a strategy which is strictly dominated. Or he may think that he's playing against somebody who is maximizing against full support like cryptographic system,
I see.
and then such a guy wouldn't play weakly dominated.
So this is part of E.
Yes, yes. So E contains all of these things. Everything is contained. Okay, so now, and then, okay, so in this terminology, how I look at solution concept, I say, okay, so I'm trying to plug in different epistemic pictures and see what behavior they generate, and by that I say, okay, so if some behavior is systematically generated, then epistemic picture is a foundation for the solution concept. Okay, and then I study how this epistemic picture affect the behavior.
The epistemic picture is a foundation for the solution concept.
Yes.
So an epistemic picture has some characteristics. What could be?
Just a list of statements.
Yes,
So-
yes. But so that's very general. So how
Yes.
can something be a foundation for a solution concept? I don't know.
Well, it's just in general when you take epistemic paper in the literature, right? They provide some. They call it epistemic conditions. For example, epistemic conditions for Nash equilibrium.
Right.
Okay, so now in my model I call this epistemic picture with slightly different interpretation. So in the existing literature they look at it a little bit passively. They look at it, okay, so suppose somebody happens and could be this and what. In my paper I view it actively. A player takes it and he works it and he really works as an algorithm. Input is his epistemic picture, output is his decision.
Okay. So if I read, for example, Aumann and Brandenburger, I think epistemic conditions for Nash equilibrium, I can tell what they say in your framework.
Yes, the guy with the last slide.
Okay.
Okay. Now, okay, so what do I show in the paper? I will not be able to show everything here, especially with proofs, but proofs are not that difficult actually. Mathematics is simple. Construction is a bit involved. So now, okay, so I established three types of results, or robustness results using epistemic, and something which I don't think is visible with existing frameworks. So, one thing, imagine that you're a mechanism designer and you're designing a game and you're telling your participants what they should learn, what we should know, and how they should behave, right? So you design a system, okay, but suddenly some of your guys, okay, so instead of playing according to how you suggested, actually learn something about the game a little bit more. Maybe he learns about his opponents, maybe he studies more and things like that. So a good thing to have is that his behavior would be still within the required prediction. He would not try to outsmart and play something outside and break the rules. Okay, so in my framework, it would be something like saying, look, suppose I have one epistemic picture and generates a set of behaviors. Now, I want to have a situation that if the guy actually has a more precise epistemic picture, which has more information, that the resulting behavior is monotonically smaller as a set.
Precision is the.
Precision I will define for me.
Does it have to do with cardinality of E?
No, it's syntactically. Okay, so I'll show.
How can it be? Suppose I choose the top, and then I get more information.
Well, suppose you are designing the rules of how to drive on the roads. Okay, so you give everybody the driver book, and you say, look, this is how you do, and everybody on the road learns this thing, and so on. And okay, so if you're happy, everybody just follows these rules. But maybe after a while, what happens, they develop some kind of social norm, thinking, okay, so if there is a traffic jam, this is how people behave. Okay, so they learn something more about each other. And the good system of rules would be such that, suddenly they wouldn't start systematically breaking the rules. So I want the solution concept to have this property, this kind of robustness. And this is how I do it. Okay, so we increase precision, picture contains more information about the world, the guy doesn't start breaking the rules.
Okay, my question is simple. Suppose I look at my epistemic picture and I decide to play top. That's it, no
Yes.
set of actions, just
Yes.
top.
Yes.
Isn't it possible that you give me more information and then I say, okay, I play bottom instead?
And that would be bad. That would be not robust. That would be bad. Okay, so I'll show you sufficient conditions for robustness in this case.
Okay.
Okay. Now, when to expect a robust behavior? What you described is not going to be robust. I want to avoid. Another thing which could happen, look, I give you this kind of rules and I expect somebody is like, everybody in society between 2 and 3 levels. And somebody, some very smart comes up, 10 levels, and start outsmarting and start breaking the system. I don't want that either. Right? I want decreasing monotonically prediction in a level of player, like in strategy elimination procedures. Okay, so I give sufficient conditions for that. And finally, there is a Colbert-Martin question in which we have a dynamic game with perfect recall, and you could represent the same normal form with different trees. Okay, so and the question of normal form invariance is just we want to have a solution which is invariant with respect to different representations. So I provide sufficient epistemic conditions on the solution concept to be invariant.
Decreases refers to the set of strategies, the outputs.
So which one?
No, the verb decreasing.
Yes.
What's decreasing?
So as the level of the player goes up,
Yes.
the set of strategies which he can play monotonically shrinks.
That's not bad.
Yes, and so this is about decreasing, and this is just invariance, the same way how Colbert and Mertens understood it. Only they gave mathematical solution, I give epistemic solution. Okay, so these are the 3 main results, and then some applications. So I look at, I try to rewrite different strategy elimination procedures. Then I look at Aumann and Burger precisely, and then also there is a paper by Samuelson on common knowledge of admissibility. He reports some problems within the partition model. Okay, so I look at it, how it translates into mine. So I'm not going to present everything here, but it's in the paper. Okay, so let me give you a simple example, and if you understand the logic, I think this is basically, okay, so this is how I thought 10 years ago. The rest took me to write it down. But this is, I think, is very intuitive. Okay, so suppose we have an involved they play game, G. Okay, so some simple matrix, and has 3 strategies, Bob has 2. Now I say, okay, so now because I have layers, levels of reasoning, right? I want to distinguish between optimality and rationality. Because optimality is like in Savage. I take just expected utility maximization. Okay, so when I say in this paper optimality, it's a classic Savage type of optimality, one's command. I distinguish it from Maximino optimality, from cautious optimalities, from sequential optimality, other things. But when I say rationality, this is how I understand it. Rationality is only from the point of view of a player who understands the situation. He can say, my opponent is rational. What it means that if I'm level 5, I say you're rational, means that I ascribe to you level 4. Doesn't mean I think I'm smarter than you. This is just the highest level I can possibly compute for you. Okay, so sometimes in level P papers they say, well, maybe people think they are the smartest one. Here I say, no, not necessarily, it's just like, maybe I think that you're level 10. I just could not possibly compute more.
But why you trust, but why you take a decision based on the belief that he plays level 4? Because if you assume that he can play level 10, maybe the optimal action should be something different.
Sure. So here comes my result number 2, right? About levels of this one. So in those situations in which theorem 2 applies, I will be happy because okay. So this is how you play if you're level 4. But now at least I can understand if you're level 10, you're playing somewhere within that. At least you would not surprise me by doing something unexpected. Okay, so now, so let's take this translation of the words optimality and rationality, a little bit informal still, and let's say that, okay, so again, informally, N thinks that there is a common knowledge that this game G is played. So I'm going to translate it in the paper so far Twitter. There is common knowledge of optimality. I think that you are expected utility maximizer. I think that you know that I'm expected utility maximizer and so on. And common knowledge of rationality in this particular sense. Meaning that if I'm level 5, I know that you're level 4, and I know that you know that I'm level 3, and so on. With this translation. Okay, so what should he play if her level is k as a function of k? And I'm also going to be doing that simultaneously for Bob as well. So she's going to be thinking about Bob and so on.
A1.
Huh? So K0, okay, so K0, everything is possible for M. For Bob, E1 is, okay, so this is what she does, right? So she starts looking at Bob. Bob can do everything. But now she's level 1, she only considers him to be level 0. Okay, and then she considers possible descriptions of states, and the states in my model, they can be actually written as a set of propositions which are true or false. Yes, so some non-divisible propositions. So for her, state is a combination of two propositions. Bob is level 0 and what he plays. So Bob is level 0, he plays B1. Bob is level 0 and he plays B2. And now she looks, everything is possible. And now as she constructs the decision problem, okay, so she has three acts, A1, A2, A3, and these such waves. And now I say she must be optimal, so what should she optimally choose? She optimally means expected utility maximizer. Of course, we know by David Pierce lemma or by some other results, she can play every strategy which is not strictly dominated. Okay, and here A3 is strictly dominated by A2, so we can drop this one. When we think about Bob of level 1, he also analyzes that, assuming there is common knowledge of all these things, so his picture is very similar. So he cannot dismiss any of his situation. Okay, so that's going to be our predictions about level 0 and level 1. So if Anne is level 0, she can play everything. If she's level 1, she can only play this one. And for Bob, he can play everything. So now let's think about N with level 2. So she says, okay, so now there potentially could be 4 different states. Bob is level 0 and he plays B1, Bob is 0, he plays B2, level 1 he plays B1, level 1 he plays B2. So she starts with all these considerations. And now she says, look, I know that he's rational. That means I dismiss the first two. Okay, so she throws them away, and what's left is just, okay, so Bob is level 1, he knows G because it's common knowledge, he knows that he plays G, and he optimally plays B1. He knows G and he optimally plays B2. And then she said, is it possible this or that, based on what I know? Both of them are possible.
You have some probability distribution over here?
And then she forms probability distribution. Okay, so the first step, she says what's possible, okay, so W3, W4, and then the second stage, she creates probability. But she can take any probability because she's not restricted by any other statements. So all of them are possible. And again, you know, she can play A1 or A2 because it's the same acts. Okay, so for her, so far so good. For Bob, actually, if he is level 2 and knows common knowledge and all the stuff, right, he can dismiss strategy B2. He will not play B2. Because it's going to be for him, this situation looks like that 1, 2, 0, 1, and he will take 1, 2.
Like you have to iterate the
Yes, and you get rationalizability. The result, and okay, so let me do one more last step. So, okay, so now the third level, right? So she now considers 6 different states: level 0, level 1, level 2, and B1, B2, B3. So because she knows he is rational, she dismisses 0 and 1. So what she's left with 2 possible states, in which Bob is level 2, and he knows that G. Anne is level 1 because he knows she is rational. And she plays she's optimal and she's not G. And he optimally plays B1. And Bob is level 2, knows everything this about G and An, and he plays B2. But now N concludes, he does exactly the same computations which I did on the previous slide. She concludes that it is impossible for him to play B2. Okay, so she strikes out this state, this state. And what she's left is she's only left with one state of nature in her conclusion. And now she has three acts, right? A1 pays 3, A2 pays 2, and A3 pays 1. What she chooses A1. And the same for Bob, and if we continue doing this logic, right, we continue, we of course generate in general game, we generate rationalizability procedure. Standard one.
Is it always true that, like here, when you have 2 in red, then it's also 1 and 0?
Sorry?
When you have 2 in red, say at the bottom, at the margin, the numbers in the margin, where it's 2, you have a 2.
Yes.
Is it almost automatically also 1 and 0 if it's 2?
What's 1 and 0?
Meaning that it will be chosen also if Bob is level 1.
No, so okay, yes, yeah. Well, if the prediction is decreasing,
Oh, so yeah.
yes, so the rationality procedure is such. But if you take common knowledge of admissibility, it's not going to be decreasing, so.
Oh, I see.
But yes, so right now, so basically, okay, so what I'm saying here right now, look, common knowledge of the game, common knowledge of optimality, and common knowledge of rationality provides epistemic foundation for rationalizability procedure of Berkheim and Peirce. It's no surprise, it's quite similar to what they wrote. Okay. Now, today I want to formalize all of these notions which I wrote here, and also do them much more general. Okay, but the basic idea of the algorithm is kind of like, this is how it works.
But rationalizability is what we get when we assume what? We assume rationality?
Usually they say it's a common knowledge of the game, common knowledge of rationality, but they do not model what's common knowledge of the game. And they do not distinguish between rationality and optimality because they consider perfectly rational players.
Okay.
Here I have bounded rationality and I distinguish between how much deep you think and whether or not you take optimal action with some reference.
So this is just an example of what we can do with your flame.
One very special case.
You can do anything.
Yes. So it turns out you could formalize it and do much more general. And this one is simple. The other one is. So now, okay, so how it relates to the literature? So basically, there is several epistemic models. They can be categorized into two broad categories. One is a partition model, which started with Allman, and a little bit with Joseph Feinberg's, I also put it in partition model. And then there are type structure models, the idea of Karasani of infinite hierarchy of beliefs. And then Mertens Zamir, Brandenburger Deckel, and a good survey by Deckel and Sinskal. Okay, so they coming back to the question, bounded level of reasoning is by no means new. Yes, Batigali talks about it to simplify extensive form rationalizability. In the epistemic context, William and Katz tried to do something with them in the type structure model. And the idea of my level is closely related to the cognitive hierarchy model from Mikhail. From Mikhail. Now, okay, so also from some old ideas, like besides the, so this is an idea, and also there's a couple of ideas from old literature 100 years ago. It's kind of philosophically how it feels. It's Tractatus of Wittgenstein, in which when you think about state of the world, the state is a collection of facts, some non-divisible facts which can be true or false. Okay, so it's a collection of zeros and ones in places. And a player makes to himself such states. We make to ourselves pictures of facts. This was basically two ideas, the rest is not Wittgenstein.
But the state of the world is not a concept of Wittgenstein, right? He doesn't
No.
use the notion of a state of the world.
Because he only has one. He didn't consider, it was in 1922, before Savage. He didn't consider either different possible states. He did not deal with the problem of uncertainty.
I see. But the notion that the state of the world is the set of all sentences that are true in that state.
Not sentences. So here is the thing. So you're thinking about a little bit further in logic, right? Symbolic logic in which you have different formulas which can be derived from a given alphabet and connectives. And you say, okay, so my state is just all these formulas which are true. Okay, so that's a little bit later. This one is much more simple. This is just okay, so I say, look, I'm only dealing with, say, 10 variables, 10 different things I want to consider, and that means my possible state of space is 2 to the power 10. Okay, so I'm not considering which formula is also true. So it's more primitive in this.
Well, one seems to be kind of a hybrid, syntactic, semantic.
Yes, it's gonna be. Okay, so now, okay, so if I were to compare models with the existing one, this is what I think my model is good. In these 5 different dimensions. Okay, first, it's Bayesian in the sense of Savage, in which I clearly separate state of the world, which is extraneous to the player, from her or his actions. Okay, so I want to do this separation, Bayesian separation, which Savage wanted to do.
Ask something. So I'm not familiar very closely with the literature.
Mm-hmm.
So I have 2 questions. It's not a criticism, but during the last 20 years or more, there is no relevant paper to what you do? Or?
Well, this is okay. So this is 1 and this is 2, but nobody tried that. No, this is a completely new.
Okay.
Well, the close one, okay, so is basically I mentioned. Well, there's a lot of empirical game theory literature on bounded level of reasoning, but they're not trying to formalize knowledge, belief.
So, and the second question, I'm trying to understand, your contribution is by suggesting one model to analyze bounded rationality with k levels, and what is exactly the point that you would like?
So I'm proposing a simple model, and so let me tell you what's good about the model, and I'll compare it with the existing models.
Okay, because taking into account that we are not very familiar.
Okay. Yes. So the first thing.
Just a second, please. What did you say about Savage in the previous slide?
So the Savage is basically one of the main ideas in Savage. The way I read it is just he proposes when you deal with uncertainty to separate what you can affect, what you choose, what you are the master of, from everything else in the world which you cannot affect by your decision. So this kind of like orthogonality, this thing he proposes, and I want to keep this.
I think you refer to 22 paper, you may want to take the century.
Yeah, sure. But this is like.
I also thought
It is a shit.
2022. By the way, Wittgenstein later in his life did not like it.
Yes.
Went a completely different direction.
That's alright.
But you don't know.
Okay, so.
And the key, my last question, and the key ingredient in your paper is the robustness that you showed?
Well, not the key. Okay, so I'm building up a model, and then and then I'm able to show some results which are not feasible even in the recent epistemic frameworks.
Okay.
So the types of robustness.
So you are going to elaborate on this slide that you
Yes,
showed?
yes,
Okay,
yes.
so I'm good.
Yes. So I have like 30 minutes, right? Okay. So another thing is the model is going to be finite. If you give me a finite set of statements, so countably infinite, I'm going to be working with finite state spaces, which is nice. I don't need to rely on topology or some subtle assumptions. It's going to be inductive, which sometimes actually helps to prove something. You could prove theorems by induction. it's universal in the sense that I could actually plug in any types of preferences, any types of facts, statements about the game, and general modalities, assumptions from belief, no problem. You throw at me a new type of preference or a new type of epistemic modality, I can elaborate without changing the algorithm. For example, and another thing is it's direct. Okay, so this is I need to explain. So the way the theorems will work, the input of the theorem will be a statement about statements which are written in the language of a human. And the output of the theorem is how it affects the behavior. There's not going to be intermediate steps in the statement of the theorem. The intermediate one is going to be the proof. Okay, so compare it, for example, with Alman 76, which says if players have common prior and so on and so on, they cannot disagree. But then what exactly is common prior is not, it's a intermediate type of thing.
What do you mean to
It's not like if you go on the streets, if you go in place where players play games, they don't know what's common prior.
Do they know their own priors?
No, but they don't understand the concept of prior or the prior stage. All of that it's endogenously built in the model. But for example, so compare the statements of Allman theorem and the statement of Modigliani-Miller. Okay, so in Modigliani-Miller they say, for example, if there are no taxes, if there are no frictions, fees, if everybody can borrow and lend at the same rate, then blah blah blah, value of the firm doesn't depend on the capital structure. The whole inputs are well understood in economics without financial theories. To understand Allman 76, you do need to study his model first.
But knowing rationality is, you think, is more immediate than the priors?
I think so.
Why?
I don't know. It's like, to me, it's I don't understand what's priors. To me, it's not. Well, it's my personal thing.
Okay, so you say?
Well, for example, okay, so let me compare with type structure. Oftentimes they say, okay, so suppose I have a player with infinite hierarchy of beliefs, which is already pretty hard, but that's fine. And then we say, okay, so if this type lives in a belief complete type structure, then he can play that. This is strange. This is what's complete type structure, what's not, and the type structure itself is some way intermediate step. I don't
How
want to
do you solve this problem? You also suggest that there are a list of statements, and they can also define it in the same way.
But the way at least I say that, look, a player actually, this is his input, this is how he works, and the output is just what he behaves. I think this is a little bit more direct.
So the players in your model do not have to battle themselves what is common knowledge, what common knowledge.
No, they could think it through. My theorems are going to be in terms of, okay, so what if we change the statement such and such? This is how, it's not going to be about intermediate steps and procedures in the model. Okay, so now, okay, so, and usually, okay, so for example, if you have Allman, for example, well, Fargul criticized, right, so he says it's not Bayesian, for example. If you have type structure, typically, but then, for example, at least Allman, okay, so it's usually finite, at least in papers, even though it's 1989, the last one, well, usually like Allman 87, Allman 95, Brandenburger 95, they deal with finite state spaces.
You're talking about the priors here or about?
About the model, finite omega.
But it's been extended to infinite.
Yes, yeah, sure. I understand you could expand it, but you could receive meaningful results on finite state spaces.
What do you mean? People have created infinite models of all these things
I
over the
understand.
years.
Well, so here's what I mean. If you take a type structure, Burger-Neckel, and you want to obtain some meaningful result about rationalizability in a 2x2 game, you must work in a belief complete type space, which is infinite.
So,
Then it's necessarily infinite.
yeah.
Allman 87, you could work with finite and obtain something else. in that sense. And mine as well. You could work with infinite. I'm saying, okay, so I could write something meaningful with finite.
Yes, that's different from saying it's only meaningful if it's finite.
No, yes, it's different. I'm not saying that. Yes, now, okay, so before we go into the model, actually, now I need to do syntax, right? I need to write down everything formally, and I'm gonna do it a little bit quick. But okay, so basically, there's gonna be a language. There are several languages I use in the model. This is the most primitive one. This is the most simple one in which I can state theorem 1 and 2. For theorem 3 invariants, I need to use it extended to another language. But I will show you this L0. So it consists of 4 parts. The first one is symbols for things, basically names. Then atomic facts, epistemic modalities, and rules how to form statements. Okay, so symbols, they, in this simple language, they only consider 2 types of names. One is infinite set of names for players, another one infinite set of names for strategies. Okay, so countably infinite is enough if you want to describe finite names. Now, atomic facts. So here is going to be a deviation from logic, standard logic which you're used to. Usually they have some atomic facts, like they write it as a letter and it's colorless, it doesn't have any characteristic. So now I want to have some characteristic. Think about a simple statement, unplaced operate in present without, unplaced operate. So now I want to have some distinction because for Bob, this is going to be the description of the state, whether she plays operate or not. So it has to be outside of his decision, it has to be in his state space. For N, it's going to be her strategy, so it has to be has to be not a part of her state space, her own strategy. So I want to keep track of that, and for that I introduce the notion of subject. The subject of a statement is the one of several players who can affect the statement. So for example, unplaced operate is going to be affected by I define it by definition. It's no more than that. It's going to be just a way to track it. Who owns a statement? Okay, and another thing, just because I have finite levels of reasoning, I don't want my players to think too deep if they're level 5. Okay, so I want to keep track of how difficult the statement is. Okay, it's going to be a level of the statement. And in this simple language, I consider only 5 types of statements, atomic facts. Okay, so they are levels of reasoning, saying, okay, so player I has level k. Okay, by definition, I say this statement has level k. So that, okay, so if I'm thinking about a player who's level 5, myself I'm level 4, I dismiss the statement. So this is why this
The statement that Mikhail has level 5 is of level 5?
Yes, it's by definition. No more meaning, just a definition. And by definition, Mikhail is the subject of the statement. Okay, so rationality, the same. All of the other statements have level 0. This is the only one which has level k. Okay, so now rationality, player I is rational. All of the other statements have subject I, except for the last one. Okay, so rationality, 2 types of optimality. In this simple language, I consider 2 types of optimality only, not LPS, but only just savage expected utility and Gilboa-Schmeidler Maximilian.
You don't need to mention the game?
Strategies and waves.
No, optimal. Even for optimal.
No, okay, so I'll show you, Okay, so far, this is just the building blocks. From them, I'll build a game. Okay, so the tricky one is the following. Strategies, okay, so everything is intuitive, I think, except for players. Okay, so here is a statement. Player I receives 5 units of utility. For simplicity, I don't think in terms of consequence, I already just fix instead utility function. You will expand the language. Okay, so player I receives 5 units of utility. Okay, so what does it mean? Okay, so it's a level 0, but by definition I put all of the players in the language to affect the state. Why? Because I do not ever want a payoff to enter a description of a state. The payoff is a configuration between my strategy and the state. Okay, so I never want to put it in the state. Okay, so and this helps me to helps me to throw them out later on. Okay, so this is just basically so building blocks of my language.
What does it mean? The subject is I. Wow.
That's just a definition. I introduce the notion of a subject and I say this is all the players which are in the game. I will use them later on.
What is the subject of a statement? Not why it's I.
This is who is the subject about.
It's about. And here it's about I, small I, but it equals capital I. Why?
Yes, capital I, all of the players can affect the payoff.
But the other players too affects the payoff.
I receive 5 units of utility. Why? Because
Oh.
I chose something and you chose something. We all affected it.
Okay, so everyone is the subject. Okay.
And I cannot put my payoff in your state space or my state space. It's some way at the intersection, right? I want to throw them out. Now, okay, so epistemic modalities, here in the simple language I only use 2 types. This is just knowledge denoted by K, just a letter. And I'll tell the semantics later. And P belief. The probability of at least P that something happens. Okay, and then usually, as usual, MI means that player I model where M that. For example, K1 means that player 1 knows that. It's a simple notation used there. Yes, now, statements in this language are constructed from atomic facts through applications of logical connectives, brackets, and application of epistemic modalities. Okay, but they are constructed according to some rules, and there are 6 of them. So here are the first 4. First of all, okay, so statements as atomic facts, they will have levels, and they will have subjects. Okay, and I will keep track of them. And besides that, I also wanted to keep track of variables. So the statements, think about it as each statement is going to be a propositional formula, as in usual logic, and it's a propositional formula of some variables. Yeah, and this is going to be variables in propositional logic. Yeah, I'm also going to be defining them by definition.
What is a variable?
Well, okay, so say you have a statement A and B, or not A. The variables are going to be A and B.
In Q.
No. Now, okay, so the first 4 rules, they do not use epistemic modalities, but they can be applied to statements which have epistemic modalities. Okay, so atomic fact is a statement, the variable being itself, and level and subject the same way as we defined previously. Now, brackets can be applied to a statement without changing level, variables, or subject. Now, simple negation. In this simple this is just to obtain theorem 1 and 2. This is needed. For other languages, for other theorems, you could drop it. You could expand, but here what I need, a statement will have variables, and some of these variables are going to be atomic facts, and some of them are going to be epistemic statements to be defined later. So if a statement is only a function of atomic facts, then I can negate it. But I cannot negate statement like player 2 believes something. I cannot say not player 2 believes something in this language. In others, I allow. Okay, so simple negation, and okay, so if you negate, nothing changes. The level subjects and variables.
Why do you rule out he does not know something? Why?
Well, it's just to obtain theorem 1 and theorem 2 only. But for theorem 3, you could expand. You could allow any negation. And also to obtain theorem 1 and 2 monotonicity results, I only use monotonic connectives, meaning and or, but not imply, not arrow, only monotonic. Okay, so now already with these simple rules, I can construct you rules of a game. Okay, so here is the rules of the game are constructed from two very special types of statements. Okay, so the first one is strategy rule. This is basically saying, look, here is a set of strategies, and here is a player. And I'm saying this player plays exactly one strategy from this set. This is how I write it in usual logic. Okay, and what's important here, I also like the order of the things matters, how many brackets matters, and so on. If you, for example, if you draw one more brackets here, it's not a rule of the game. So I just fix some statements and I designate them and I say, whenever my computer or player finds them, he immediately recognizes this is a rule of the game, potentially. And nothing, something else is not a rule of the game. A payoff rule is, again, this is just a material implication. It's basically saying if they play some kind of I think this should be E. And yeah, conjunction. I'm sorry, but okay, so it's a typo. But it's basically if they play some strategy profile, he receives this payoff. Okay, and the way okay, so it has all of them has level 0. The set of players who affect, just the last one is all of the players because of this payoff, not just the players in the game. This one is only the player himself. Okay, I call them the rules of the game. And here's how I can construct the rules of prisoner's dilemma. It's gonna be 10 statements. It's 4 statements which describe, 2 statements which describe sets of strategies for either player, and for each player 4 rules which describe his path in each cell. Okay, so that's rules of, and then after that I can say, look, the player knows the rules of the game. Okay, so now why I want to designate this statement specially, because usually when I apply epistemic modality, I don't want this language to apply it to a statement which talks about myself. I do not know what I believe. I do not believe what I know and things like that.
Why?
You don't know what you know?
I don't know what I know. I do not have all these axioms of knowledge. It's not like, no. That's just completely out of this. Not positive introspection, not negative introspection, not axiom of truth. Nothing like that. So it's a different one. But the thing is, okay, so the only exception which because I want to say that rules of the game are common knowledge, I want to say something about my payoffs or about my strategy set. I want to allow the player to know the rules of the game. For example, okay, so say I know that I play either left or right. That is already a restriction on my freedom of choice. Before I do something, I know I must play left or right. But okay, so this restriction is in the game, it's the rule of the game. So I allow this one, and this is the only exception. So here are the two things.
Do you have any use for the case when there's no common knowledge of the rules of the game?
Sure. You could apply that as well.
Is that an interesting possibility?
So I did not use it in the paper, so my theorems are quite conventional, it's common knowledge of the game and so on. But I do think that you could extend it. Like, for example, you could extend the language to allow for incomplete information and maybe obtain something beyond cosine 67. Because it's a finite steps, you do not obtain this. So there's a possibility I did not explore it. Okay, so now basically the rules is that, look, non-introspectively I can apply modality. If I have a statement of which I'm not a subject, I can apply any modality and say, okay, so I believe this. Okay, and what happens is just the level of the statement goes up by 1. So the level is basically how many modalities and maybe levels. Variable itself is a statement. So this is going to be called epistemic statement, the one which has this form. The epistemic statement itself is a variable. And the subject is myself. I believe that you do something, the subject is only myself, not you. Okay, the only one to which I can apply knowledge introspectively is the rules of the game, a set of statements which I call out 0.
So I believe that you believe. I can say that.
Yes.
is the subject?
You. Because it's a statement about you, this is what you do, you believe. Okay, so now.
What does it mean that you don't have, that you don't assume that I know what I know?
You just have prohibited. I prohibit such statements, I do not write them.
So doesn't it change the definition of common knowledge? I don't understand.
It's a different notion of knowledge, it certainly doesn't just apply this,
So-
so that doesn't have this, it's
How do you define common knowledge?
Okay. Okay, so now epistemic, okay, so a few minutes finished. Epistemic statement is a statement which has this form, right? And the important thing is going to be pre-variable with, it's basically the variables of what's inside. This is the pre-variables is going to be from what I'm going to be constructing the state space. Okay, so now, because I apply conjunctions monotonically, every proposition which I can write of its variables is going to be a proposition of about atomic facts and epistemic statements. Because I don't apply negation to epistemic statements, one can show simply that I can write down a predicate, a full function of variables, if and only if it is increasing in its epistemic variables. This is going to be important for theorem 1 and 2. Then, okay, epistemic picture is a collection of epistemic statements of player I. Truncation of epistemic picture. Epistemic picture could have many levels, very long sentences. If I'm level 5, I only look at up to 5. That's a truncation. And the picture is finite if all of its truncations are finite. So basically, level 5, very important this finite pictures because, well, if I have a finite picture, I'm going to analyze finite many statements, I'm going to construct finite omega.
Finite truncation, what does it mean? Every statement is finite.
Yes, but you could have many of them. You could have infinitely many. And if you have infinitely many statements of level 3, then your picture is not finite. But common knowledge is a finite epistemic statement, right? Okay, so say S is a set of permissible statements. Okay, so I write down as usual in class what's common knowledge, right? I iterate, okay, I1, I2, IN, and all of them statements is a union of them. And then I throw out those which are not permitted by application of modality. I just erase them, they do not exist. And this is not an epistemic picture yet, because to get an epistemic picture from this thing, for example, I only concentrate on those which start with player I knows. So, and this I interpreted. Player I thinks that it's a common knowledge among player I large, that P. This is just the definition and just a list of statements. This is how I define common knowledge.
CKIP. Explain what this means on
This one?
No, go on.
Okay. Yeah, it's a list of statements. It's infinite list of
What's on the right side of the equality?
KI1 knows that KI2 knows that KIN that P. And I can write it down for all sequences of I1, I2, IN for all n.
Observer can know that he knows because he
Yes.
himself.
Yes,
You
and
said it-
now I throw them out. Those which are not.
Which are what? What is that?
I throw them out, they're not included. Okay, so this, so far, it contains player knows that he knows that he knows.
Yeah.
And then I say, look, those which violate my rules, I throw them out from the list.
Why? Why?
Why? Because it's my model. No reason for this.
Which ones are owned out? For what kind of?
So this one, okay, so for example, I cannot say like player 1 knows that player 1 knows that something. Okay, so I throw such statements out. Player 1 doesn't know that he himself is Russian. Oh, maybe he doesn't consider such statements.
He has no mirror. He cannot see himself.
Whatever, just it's a model. And then eventually I'm looking at the game only from the perspective of one player, and I say, look, I'm only interested in the statements which start with player I knows. Okay, so this is what I define, and then I could apply. Okay, so it carries a common knowledge of the game. It's just the rules of all the rules of the game. This is the player knows that all the rules, and then also I can define the rules of the game of common knowledge. Again, also a list of statements. Nothing else. I'm not giving you semantics yet. There is a common knowledge of rationality is the same way. All of that is can be written, and all of these features are finite. If you can deal with finite statement players and finite games. Okay, so all of this is fine. Okay, so now the model really quickly actually, but because I'm feeling running out. Okay, so to describe how a player thinks and how he computes what happens with other players, the critical thing is going to be possibility function, which answers the question: if player I has optimality type opt and level k, and is given epistemic picture EI, can he play strategy S? And the answer is either yes or no. If he ever can play, then the answer yes, true, otherwise the answer false. And my main assumption is a player with level k can compute this function pi for all inputs with lower k. To compute that, you need some kind of recursion. Okay, so how I define this function pi and how I compute it? Yeah, I compute it this way.
Is that an assumption about the players or
Yes.
about?
This is what means level k. Why it is difficult? Why is it? It's just difficult to compute this thing. Okay. Maybe sometimes it's even impossible because maybe some function is not computable, not in computer science. But so sometimes for many epistemic features it's computable. But I do not ask this question in this paper when it's computable. Okay, so now how do I define? First, for level 0, all this yes, everything goes. And then for level 1 and higher, I think that the player uses this algorithm. Yes, so what's the algorithm? Yes, then there are a lot of moving parts. First, he constructs, so suppose we have a player with level high, some optimality, and some epistemic picture. How he constructs his decision problem? Well, he looks at the list of statements, and okay, so there are some statements which he knows some rules of the game. It better be that they do describe some game. Not missing something, not something more. Well, this is a special case in which I think that the player knows the whole game. I can expand it a little bit to incomplete.
When you say must?
Must. Yes, because if something is missing, or if I know a game and something else, I say, look, it's I'm breaking.
So this must be part of E.
Yes. But part of the E which is given is knowledge of the game. He must know the game. And if he doesn't know the game, he says, look, I'm breaking. I know what I'm doing. And he almost spits out empty set out. Now, the rest, okay, so let's say he plays game G and there's his opponents in that game. Consider all of these extra statements which he still wants to analyze. This is the truncation, k truncation of his epistemic picture minus the rules of this game. Okay, so now it better be that these statements among the prey variables do not include any other players besides G. Because I'm thinking N and Bob, I'm playing against N and Bob, and then just Peter comes. No, I don't want to talk about Peter. Okay, so assuming it doesn't break there, he looks and says, look, let me think about N. Okay, so I'm playing against N and Bob. Okay, so what can I say about N? Well, first of all, I look at, okay, so what are the statements about her which I consider? Okay, I look at all the pre-variables of analyzed statements which talk about N. Okay, and I say, look, okay, so these are the statements. It better be they do not mention any other strategies which beyond what she's supposed to play. Otherwise, I break. Okay, if they don't, if everything is well, okay, so I construct the following set of variables, which I'm going to be thinking about N, what you can do. And this is just like this minding about abstract. All of the strategies you can play in the game.
This is disjoint union?
Disjoint. Yes. All the strategies you can play. All the optimality types you could possibly have in my language. Optimality and optimality. All of the levels between 0 and k minus 1, because I'm level k. Whether or not she's rational, and all of her epistemic statements, which are mentioned in my pre-variables. So I'm also thinking about what she thinks and so on. So here is a set. Okay, so now a state of affairs for her is basically a combination of values of these facts. But now not all of them are physical. which of them are possible or feasible? Okay, so I want her to play exactly one strategy in the state. I want exactly one optimality type of her to be true. I want exactly one level for her. I want exactly her rationality to be there if her level is k minus 1. That's my definition of rationality. And this is one tricky one, right? Because I can compute what is possible for her, what is not, okay, it's better be that the state which I assign to her strategy is possible, given that her true state strategy is S, her name, her true optimality type, her true level in the state, and this is a critical one. Okay, so I look at her epistemic statements. Let's see, 12 of them. I say these three are true, other are not true. And negation of epistemic statement, what it means not true, it means I simply do not plug in into her epistemic picture. Okay, so now I compute what is possible for my opponent. Okay, exactly how n did about both. Okay, and then okay, so I construct this thing for all of my opponents, and I take the direct product, and finally apply my knowledge. And this is a semantic definition of what I mean knowledge. Well, in other epistemic models, sometimes they call it certainty. I dismiss everything which I know not true, and exactly that. And this is my state space. And then I complete it to strategies, and this is my decision problem. Then I look at all my other statements and I say, look, they only put extra restrictions on my beliefs. If I, for example, if I do not have this restriction, but by occasion I satisfy it, that's fine. Just like the statements, they do restrict, but the negation of them that doesn't. Okay, so I construct my preference and finally select for now. Okay, so now in this process, what happens? Step one deterministically determines the decision problem. There's no iteration. The iteration happens on step 2 because I can have many beliefs and I can choose many things. And to compute the value of pi, possibility, I need to iterate over these beliefs, which may be feasible, maybe not feasible. Computation. Assume, okay, so if it's feasible, okay, so let's proceed. Then the prediction correspondence is just, okay, so I plug in player, I iterate over all strategies in my language, which are possible. Okay, so this is the definition. Might be, okay, so let me show you, basically, again, very quickly, maybe 5 minutes if you give me, I'll show you 2 theorems. Okay, so what do I do with that, right? Okay, so basically, okay, so can be extended in many directions. Basically, do not change the algorithm, but plug in different languages, different optimalities, and so on. Everything works, and here are the things which you can show. For example, okay, so suppose I want to change how now I'm thinking about theorems in which a game is common knowledge. Okay, so now, besides common knowledge of the game, suppose I can add or change statements without manipulating statements which somewhere mention the rules of the game. Because the rules of the game, they play a very critical role in the first steps. They can break the algorithm. I don't want to mess with them, but I can mess with any other statements. Okay, so I call statement regular if it doesn't mention the knowledge of the game rule. Okay, and the epistemic picture which consists of regular statements regular. Now for regular pictures I can say one is more precise than another. Here is a definition, right? So one is more precise than another if you could manipulate it through a finite sequence of the following operations. You can add a regular statement, makes it more precise. You could take an epistemic statement and change it according to some rules. Okay, so there are several rules, but basically the idea is just, look, I take a statement, I replace it. I take a statement or a couple of statements, I replace it. Usually, if you look just at one player, the right-hand side implies the left-hand side. For example, if I believe something with probability 75%, at least, implies at least that same thing with probability at least 50%. It's like that. So you could check it's like right-hand side implies left-hand side. Okay, and but this is just okay, so I take a statement and I change it. That's not very interesting. The interesting thing you could do better, you could take a long statement You could look inside of that very, very deeply, and you could manipulate them. According to some rules, right hand side implies left.
What's the point of all this?
The point of that is the theorem. If you have a more precise epistemic picture, it generates a sharper prediction. For example, if you have common p-belief in rationality, it generates weaker prediction than common p-hat belief, where p-hat is bigger than p. Things like that. Or then common knowledge generates a bigger prediction. Things like that. And then also you can apply this thing to say when it is that level decreases prediction. For that you need some definition of positive epistemic picture, but then you can apply this thing as well. To say when your prediction generates strategy elimination. Then there is some theorem about invariance. Let me skip it here because I need an extra language. Applications. This is the last one I want to show. The condition financial equilibrium. So this is a two-player version of Allen-Brandenburger. This is literally their theorem. Now, okay, so they say, suppose it's mutually known that G, mutually known that players are rational, and mutually known that their assessment is phi. Then assessment is Nash equilibrium.
What is that?
F is assessment conjecture which is true in the state. Okay, so I wanted to have a bold phi. There was some conflict in LaTeX. But this is the statement. Small phi is a conjecture. First of all, I can write down what conjecture is in a two-player game in my language. So I can write out as a little statement. This is a conjecture that player I thinks that his opponent plays certain probabilities. I can write it down in my language. That means that I can translate this thing. And the way I translate it, look, in their world, they're looking at objective state space. And they can say, look, player I knows that something, player J knows that something. It's a different people. I have only one person in the model, really, imagining he's playing a game. So I need to write it down a little bit deeper. I need to write that he knows that the opponent knows that something about him. I need to add extra layer to work it out. Okay, so now, so here is knowledge of the game, one extra level. Knowledge of rationality and optimality, that's my version of rationality. And then knowledge of conjectures. And then something blah blah blah, and then it's a Nash equilibrium. But now, okay, so this extra layer actually kills the results of the result. So here's the thing. So the way I understand the paper, it says, look, to get an equilibrium, you don't need that much common knowledge. It's very
Mutual knowledge is sufficient.
it's very relaxed set of conditions. Now I put it down into my subjective framework, and what it says here, look, player 1 knows that player 2 knows that player 1 has a certain conjecture, and it better is that this is a conjecture. But now in my model, a player takes this as given and just analyzes it, and then step 2, he's free to form a conjecture. So now, to have systematically equal this conjecture inside with the conjecture that he actually forms in step 2, there must be some restriction. So my interpretation of these conditions is that a notion of equilibrium is not natural for unrestricted Bayesian players. So you do, in order to get an equilibrium, you do need a restriction on how he formed beliefs. That's a fact. So that's a different kind of answer actually. Like it's this extra layer, the way it is working in type structure model, they do have this restriction implicitly. Because when you write down this thing, that's some property about player 1 belief. And when you write down player 2 knows this thing, in my model, it's a property about state space of player 2. These are two different things, with two different objects. And in an objective type structure model, they are conflated into the same thing through the objective type space. So there is an equilibrium restriction in the type structure model itself, which this model kind of unravels. Yeah, sorry.
You want to show some summation, some conclusion?
No, there's no conclusion.
This is the last slide.
Well, basically, the conclusion you could, okay, so this is a new model underexplored, and if you're interested, I think it's intuitive, and you could try to apply it maybe to mechanism design, for low levels of reasoning, maybe to study new ways of robustness, because there's a different robustness from the one which is used in the literature.
Do you have the results of the same flavor about other standard solution concepts?
Well, I have several description of different rationalizability concepts, how they are robust, not robust, based on my theorems. And then I also, like the last section, I have a little discussion of Samuelson 92 and how it's different perspective. He has a partition model which is essentially he looks at the solution concept as a fixed point. And in my model, I approach it inductively, so different interpretation.
So which robustness notion is robust and which is not?
In Samuelson? Okay, so for robustness, okay, so in Samuelson, basically the problem is that, okay, so he uses a cautious notion of rationality, right? You need full support thing. But he mixes this with a statement like knowledge of this. A knowledge is a dogmatic statement. In order to get a robust prediction, for example, Schrödinger prediction, you do not mix caution, full support, with knowledge statements. That's a theorem 1.1, which I didn't show here, but it's in the paper. And then also another one, for example, this is how theorem 3 plays out. So look at extensive form rationalizability and literate serviceability. And suppose you have gamma two-player game dynamic. And basically theorem 3 says, look, why we look at extensive games not at their normal form. One of the reasons we want sequential optimality. We want our choice to be optimal not at the beginning, but later on. And the problem with sequential optimality, to write it down formally, we need to address elements of a tree. We need to address information sets, how we update and so on, right? And therefore, sequential optimality may break invariance, sequentially optimal solution concepts. Now, okay, so the theorem says that, look, if you want to do common knowledge of cautious sequential optimality, which means you have full support LPS at the beginning, and you update and you want to deal with that, by itself, common knowledge of cautious sequential optimality doesn't break invariance. And you break invariance either because you impose usual sequential optimality, in which you, like in Krebs and Wilson, you update, but then you throw away other elements of the LPS. Or if you, like in Selton 75, for example, in Tremingham perfect equilibrium, you think about Tremingham mistakes, which require you to talk about extensive 3 further. If you do not talk about this, or if you use cautious sequential optimality, you are golden, you have invariant solution concept. And here is how it manifests. Extensive form rationalizability, common knowledge of the game, common assumption of rationality, and common knowledge of sequential optimality. And this thing is not invariant. Imperative admissibility, common knowledge of the game, common assumption of rationality, and now the only small change, instead of sequential optimality, you have cautious sequential optimality. This one is guaranteed to be invariant. You actually do it in normal form. And also it shows you like how close these things are. Like Patinali and Catanini, they had some mathematical results saying that in almost all games they are the same or close. This is the epistemic closeness of these two solution concepts. Like they are only different by one small secret.